Okay, so here we are with the video on the questions from the final exam that deal with Chapter 6 from the textbook. Okay, so here we go with the first question out of Chapter 6. Let's start off, and as I said, I like to show you this particular window when we look at these problems because it includes our objective. Notice it also tells you what section we're from. But anyway, what we really want to focus on here is the objective of this particular question. It says identify the domain of a rational function. Okay? And what we have here in this question is a rational function. F of y equals y over y minus 12. Right? Drawing back on some of the things we talked about in that section. One was the basic definition of a rational function, which was p of x over q of x. Right? So we'll have a function in the numerator, and then we'll have a function in the denominator of the rational expression or rational function. And remember that this particular definition had the additional statement that q of x cannot equal 0. The function in the denominator here cannot equal 0, because if that were the case, we would have division by 0, which is undefined, remember. Okay, so let's look at our question. Again, the instructions say give the domain of the following rational function using set builder notation and interval notation. Also interval notation, okay? So we're going to look at this. Remember, domain can be represented in a couple of ways, and the ones we've discussed in this class were set builder and interval notation. So we will show the representation of this particular function's domain not only in interval but also set builder notation. You do need to identify on the test. You'll be asked to identify set builder versus interval notation. As we said, many functions are in many cases, the domain of a function is assumed to be all real numbers. But there were a couple of cases that we discussed where the domain was restricted, and with a rational function there might be a situation where you have an excluded value. So that's particularly true of this function right here. Notice we've got y minus 12 in the denominator. Again, what we're looking for is anything that makes that denominator 0. So we can find that value very easily by setting our denominator equal to 0 and solving. So adding 12 to both sides, we get y equals 12. 12 is, in fact, our excluded value. All right. So we've done this work so far. We've identified our excluded value. But now, how do we get the domain into the proper form? Let's first consider set builder notation. All right. Let's just go ahead and write it out here. So in set builder notation, we would use set notation. Remember, set notation is that squiggly bar there. So first in set notation, what we would do, we would identify our variable. So what we're saying is the set of all y's, and then we put this bar here, and that kind of means the set of all y's, where y will be a real number, or y is equal to a real number. And then what we would do would be identify the excluded value if there were any. And we do have one, and that is this right here. So we would say y not equal to 12, and we would end that up there with the set builder notation. Okay, so this is set builder, just to emphasize that what we're talking about when we use this set notation is set builder notation. Now let's put it into interval notation. And remember, interval notation was using the brackets and the parentheses and the infinities and negative infinities, as well as that union symbol. So this domain of this in interval notation, we would say negative infinity to 12 union 12 to infinity, right? So basically what this is saying here is all numbers to the left of 12 on the number line, not including 12, because I got a parentheses around 12, right? Not including 12. And then this union can generally be interpreted as saying and. Okay, so you just heard me equate the union symbol to and. In mathematics, that is not necessarily true. The union symbol is equivalent to or. And the upside down U, which is referred to as intersection, is and. But our use of the conjunctions and or, and perhaps everyday English, and I'm not an expert on English, but they're kind of used a little bit different between in math and logic. So I'm using the word and here to help you from an everyday English use of them to sort of understand what this domain in interval notation is actually communicating to us. So left of 12, not including 12, and to the right of 12 here, not including 12. So basically, in other words, all numbers, all real numbers except for 12 here. And this representation here is referred to as interval notation. That is interval notation. So a couple of ways to answer this question about what is the domain of this rational expression here. All right, so this next one here has to do with writing rational expressions in lowest terms here. And basically what we have here is a rational expression, right? So just go back a little bit. Writing your rational expressions in lowest terms goes to the fundamental property, which is this one right here. All right. The idea being here, A over B equals AC over BC. The idea here is that the common C in the numerator and denominator would cancel out, and that's why we'd end up with A over B, okay? Right, and going back to what we talked about there in chapter 6 was to write a rational expression in lowest terms. The first thing you would want to do would be to factor both the numerator and denominator, right? Notice that this one has already been factored as z minus 7 over z minus 1, okay? So what we would do would cancel out any common factors there. And what we have that is common between the numerator and the denominator is z minus 1. So the z minus 1 would cancel there. And what we would be left with here is z minus 7 over z plus 3. So now that one is written in lowest terms. Okay? And if you think about it, z minus 1 divided by z minus 1 is 1. So what we really did there was reduce it based upon the fundamental property there. All right, so in this next one, again, we are writing expressions in lowest terms. All right, so we look at this one. We do have a rational expression here. And again, we're going to use the fundamental property here. Remember, the first step in writing rational expressions in lowest terms is to factor both the numerator and denominator. Okay, so if we look at that numerator, that one is actually a difference of squares here. So let's go ahead and go to our next step here and write that numerator as a difference of squares. T squared minus 5 squared. And then we want to factor the denominator as well. What we can do to that denominator is take out a greatest common factor of 6. So let's go ahead and take out a greatest common factor of 6. And that leaves us with 6 times t minus 5. Because 6 times t is 6t. 6 times 5 is negative 30. So there we go with that. And then, so we're going to draw upon a little bit of knowledge from chapter 5 here. And that, remember, was that the way to factor a difference of squares was x minus y times x plus y. Basically, the square root of the first minus the square root of the second here times the quantity square root of the first plus the square root of the second. So let's go ahead and go on to our next step here, which would be to factor that numerator. And as we said, that would be t minus 5 times t plus 5, right? And we'll keep what we have there in the denominator, 6 times t minus 5, all right? All right, so now we've got it factored. That was our first step. Our next step will be to cancel out any factors that are common between the numerator and denominator. As we can see, the t minus 5 there is common between the numerator and denominator, so that would cancel out. And so our result here would be t plus 5 over 6. All right. So now we have written that rational expression there in lowest terms. All right, so we're coming to this next one here, which is the last question out of chapter 6 that'll be on the final exam. And I suppose it is kind of a bit of a doozy, so to speak, because it draws upon a lot of different concepts. So basically, if we look at what it asks us here, it says perform the indicated operation. The operation here is subtraction. Look at our objective. Add or subtract rational expressions with different denominators. So it's drawing on a lot of different things here. All right, to do this one, we're going to draw on a couple of different concepts and focus on these two big concepts here. So, for example, when we're coming to very simply adding and subtracting rational expressions. So, if we had a over b plus c over b, that would actually equal a plus c over b. That is, we keep our common denominator here, and then we just add our numerators. And then there's also the idea of subtracting these things. So we would have a over b minus c over b, and that would be a minus c over b. Again, we keep our common denominator there, and we would subtract our numerators there. So those are the two big concepts that we're going to draw on here. All right, so as I said, we're going to focus on these. There are additional concepts on rational expressions, specifically the least common denominator and finding that least common denominator. that we're also going to draw onto. In this particular video, I'm not going to go into detail on that, but there are a couple of resources in the Canvas course and your textbook that you can review to bring you up to speed on where we're headed with this one. So let's go back into the Canvas course. All right, so we are in our Canvas course. If you remember, we did do a video quiz on this concept, and it was reviewing LCD, LCD being the least common denominator. So if you already did that, you can definitely still go back into it here. And as it says here, we can review our quiz results, or we could retake it, and it would take us through. Okay, so I wanted to put a little video that went a little bit more. Well, anyway, as you can see, you could go back in there and retake that quiz if you wanted to review some concepts. Also, another resource, perhaps the best way to start would be to go into our Chapter 6 module here. Chapter 6-7 module, by the way. Look at our 6-7 module resources, scroll down to Chapter 6 videos to watch. Scroll on down to this particular video, adding and subtracting rational expressions. So there are a couple of things that you can review to help you with this particular question right here. Okay, as I said, we're going to draw on these concepts. Basically, what we're doing here, we're going to be subtracting two rational expressions. So we're going to be applying that rule there. But we've got to find a least common denominator here before we can handle those numerators. So in other words, we just can't start subtracting our numerators. First, we have to create equivalent rational expressions before we can do that. In other words, what we're looking for, again, is a least common denominator. So let's first ask ourselves, what is this LCD going to be? So remember, the LCD is the product of the factors in all the denominators raised to the greatest power occurring in any denominator. So first, notice our denominators are already factored, and notice they only occur once in each denominator. So in this case, our LCD is just going to be the product of these two denominators here, which would be x minus 7 times x, the product of our two denominators there. All right. So now we've got to write these two expressions over the least common denominator there. So let's just start here with this first one here. Again, we said our least common denominator would be the product of those two denominators. All right. So to be able to create an equivalent expression, I'm going to be multiplying by a form of 1. So in this first rational expression, what I'm going to be doing is multiplying that one by x over x. X divided by x is 1. All right. Another way to think about this, and not necessarily the mathematical way to think about it, was kind of one thing that I like to do. I look and I see I have my least common denominator here, and then in this one I've noticed that I have an x minus 7 already in the denominator, but I don't have the x part. So that means I'm going to have to take that numerator times the missing part, which is x. So what we end up with is this right here. Another one, and again, notice that basically what we're doing here is multiplying it by x over x, which is a form of 1. Okay. And then again, we are subtracting in this case. And then we got to write that other one as an equivalent rational expression. And again, our least common denominator here would be x times x minus 7. So again, to create an equivalent rational expression, I'm going to be multiplying the numerator and denominator by a value over itself. in this case, I would be multiplying the numerator and the entire thing, the entire rational expression times x minus 7 over x minus 7, which is a form of 1, right? So, but as I said, one way I like to think about this is my denominator here, my common denominator here. In this particular case here, I have the x already in this particular rational expression, but I don't have the x minus 7 piece. So I'm going to multiply that numerator by the piece that's missing. And in this case, it would be x minus 7. Okay, x minus 7 times 1. Okay. So notice x minus 7 over x minus 7 is a form of 1, which is what I'm really multiplying there, right? So let's go on to our next step here, which will be what we're talking about in this case right here, and that is to rewrite the expression as a difference of numerators. So again, we will have our least common denominator here of x times x minus 7. And in our numerator, we're going to perform the subtraction part. So what we're going to have is x minus 7, okay? All right. So that's one thing you might be able to do in your head mentally, but I am including this step just to emphasize what we're doing here. So let's continue on with what we're talking about. And by the way, what we're doing there is subtracting polynomials here. And drawing upon what we talked about in chapter 4, when we subtract polynomials, what we do is we change the sign of the polynomials that we are subtracting. Or in other words, we change the signs of the subtrahend, and then we add. So let's go ahead and do that. And what that is going to, and again, we're over our least common denominator, right, of x times x minus 7. So let's go ahead and change our signs and turn it into an addition and combining like terms with two polynomial situation. So what I'm going to have is x minus x plus 7. So in a lot of ways what I did was distribute that negative sign there across that binomial. All right. So that's really going to end up, and let's move it up just a little bit so we can capture what we want to capture here. So our next step would be to perform the operation there in the numerator. And x minus x is 0, so in the numerator I'm left with 7. And again, this is all over that least common denominator. Okay. So there's my result there, 7 over x times x minus 7. All right, so there we go. Those are the questions on the final exam that relate to Chapter 6 of the textbook.